All right, so when multiplying a 2 by 2 times a 2 by 1, it's our ones that we've been dealing with quite a bit. We just take the row times the column, and then you'll add up those results. So this would be 3 times -1, which is plus -2 times 3, -6. That result will be the first element. If you did that automatically in your head, I'm good with that. But as your teacher, I'm going to show you the complete math there. Then you're just going to take the next row and multiply it by the same column. So 1 times -1 is plus 5 times 3. And then when you actually do that math, -3 plus -6 gives you -9, and -1 plus 15 gives you 14. So any questions on multiplying a 2 by 2 by a 2 by 1? All right. This one, hopefully you identified that this is the identity matrix, which we learned if I multiply the identity matrix, what do I get back out? The same thing. If you've forgotten, you can always do the math to remember. So I can take 3 and -2 times 1, 0, and I'd be left with just the 3. I can take 3 and -2 times 0, 1, and I'd be left with just the -2. I can take 1, 5 times 1, 0, and I'd be left with 1. And I can take 1, 5 times 0, 1, and I'd be left with 5. So even if you forget that that is the identity matrix, when you do the math, you get to the same conclusion anyways. So yes, there's always memorization in math, but if you forget, the math always maths. Right? That's why I like it. All right, C does get more work, so it can become a little bit more taxing in how much you have to do. But the same process, you're going to take the first row and multiply each column. So 3 times 1, -2 times 2. So that will be the result of the first element in the top left-hand corner. I will then take the first row times the second column, and 3 times -3 gives me -2 times 4. Then take the second row and multiply each column. So 1 times 1, 5 times 2, 1 times -3, and then 5 times 4, 20. Again, if you're adding those in your head, by all means, I'm okay with that. It can be easier to write it like this just so you don't make any mental errors. But either way, it works for me. 3 plus -4, -9 plus -8, 1 plus 10, -3 plus 20. Questions? All right. D looks complicated because it's like letters, but the math doesn't stop looking the same. I'm still going to take the first row and multiply each one of these columns. And when I do, I'll get 3 times A, which is, and then -2 times C, which is, that would be the answer. I cannot go any further. I cannot simplify that. So that would be the answer for that element. Had I known what A, B, and C is, or D, I could plug that in and get a single number out of it. When I do the same thing over here, 3 times B is, and then -2 times D is, and again, that would be its answer. And then do the same process with the next one. 1 times A. Good. I don't take off for writing 1A, but just note that it's just an A. And then 5 times C. Biggest mistake students make is they forget the plus sign. If you get a positive result, don't forget to write a plus sign. It's not its own independent element here. These are combined. 1 times B, B, and then 5 times D. So we say plus 5D. Yeah. And there's your answer. No, I get it. But a lot of students forget the plus sign altogether. And then they keep trying to go further and they try to multiply. And I'm like, whoa. Because that one simple forgetting the plus sign causes them to go too far with it. Any questions there? All right. Plus, if you remember, we just take each element in its corresponding place and we add them up or subtract it if it's a subtraction. So 3 plus 1 gives me -2 plus 0. 1 plus 0. 1. Good. 5 plus 1. 6. So do note, even though I multiplied by or adding the identity matrix, it did not give me the same number. What do I have to add to get the exact same? What's the additive identity? All zeros is the zero matrix. So just because I'm adding the multiplicative identity matrix does not mean it will still give me the original matrix out when I change operations. And then we just kind of keep going through this. 3 plus 1. -2 plus -3. 1 plus 2. 5 plus 4. Still good? All right. Same process as before. The operation does not change. You just get a different looking answer. So it's still going to be 3 plus A, which will be written as 3 plus A. How would I write the next one? Very good. And the next one? In this situation, the 1 is important. I cannot just write C. This is a 1 plus C. The only time it wouldn't be important had it be a 0. If I had 0 plus C, then I could just say Z. 5 plus D, again, would be written as 5 plus D. Any questions on that one? All right, on the last question, can you add the two matrices in part A? Why not? Very good. No. That is for multiplication. So with multiplication, a 2 by 2 times a 2 by 1, these have to be the same. So therefore, I get a 2 by 1 as an answer. But if I'm adding a 2 by 2 to a 2 by 1, I don't have the same corresponding elements to add. So therefore, I cannot. They have to be the exact same matrix size. So no, because the size of the matrix is different, or anything along those lines. Okay. Questions? Feel good about what we learned before Thanksgiving break then? All right, today we're going to talk about the area. So we have we have taken a square before and we have done transformations on it with rotations, dilations, reflections. We've kind of jigsawed it a little bit. That's not a normal transformation that we have, but it changes the area of it. I'm going to show you a quick, easy way to determine that area. But before I release that information, we're going to go a very long route with it. All right? Makes sense in a math class. So a real hard, complicated way. Then at the very end, it's like the credits. When you've been waiting, watch the whole movie just to see what happens at the end of the credits. That's what today's going to feel like. All right, here we go. So in this part right here, we're going to perform the transformation on the unit square. So recall that this is what our unit square looks like. So we had a point at 0, 0, 1, 0, 1, 1, and 0, 1. That was our generic shape that we've always been used. So again, those are the points 0, 0, 1, 0, 1, 1. Looks like a little smiley face. And then 0, 1. Okay. And again, these points just come from previous lessons that we kept on playing with. We want to take each one of those corresponding coordinates and multiply it to this transformation to determine what the new shape is. Okay, so here we go. Let's get some math in. So we'll take the matrix 109, 3, 1, negative 2. And when I multiply it to the matrix 0, 0, remember a coordinate can be written as a 2 by 1 matrix. What will my answer be? It's going to be 0, 0. Anytime you multiply by the 0 matrix, it just gives you the exact matrix out. So therefore, there's my new point. Because at 0, 0 was the first point. So I'm going to multiply each one of these independent points to get my answers. Yes, sir. So then I'll do the next one. So 109, 3, 1, negative 2 times 1, 0. So this is 109 times 1, which is, and then 3 times 0. All right, so this just ends up being 109. I know the numbers look big, but the math's still easy. And then I do the same thing here. When I multiply this row to this column, what will my answer be? Just straight up 1. So my new point will be 109. I don't know if you just saw I did 109 ticks just there to get to this point. And then 1 about right here. That's the new point. So this point is now there. And we'll keep going through the process. So again, this will be point 109, comma 1. I wrote it for reference. And then do it again. This right here, a little bit more math, but it's still relatively easy. If I multiply by 1, 1, what am I really doing here? Well, I'm doing the same thing, right? 109 times 1 is, and then 3 times 1 is. So what am I really doing to these two elements? I'm just going to add them up, right? So 109 plus 3 gives me 1 plus negative 2 gives me. Always look for tricks and stuff to kind of save yourself some time. Again, I just wrote a whole bunch of ticks. Here's 112. And the negative 1 is going to be about right here. So now I get the 112, comma, negative 1. And then we'll do the last one. 109, 3, 1, negative 2 times 0, 1. What's my answer? Perfect. So then that comes over here. I'll put some ticks here. So there's 3, there's 2. So this is 3, comma, negative 2. So now I get a shape. Might be easier right here. Looks something like that. So we took that square, we pretty much turned this into a parallelogram. We skewed it, we made it bigger. We probably put some rotations there. Really kind of hard to tell with these kind of numbers because it doesn't give us it in radian form or degree form. So it'd be kind of hard to figure out what those coordinates are. So part B, what are the coordinates of those vertices? Well, you already have it written down. You can write them down again if you would like. And then the question is, what is the area of this new shape? For starters, what's the area of a unit square? If this square right here is 1 foot by 1 foot, what's the area of that square? So if a unit, I like it. Feet squared, technically, yes. If this is 1 unit by 1 unit, what's the area of a unit square? 1 unit, right? And you did that by simply taking length times width. Now it gets a little bit more complicated because how would I calculate what this length is? What did I have to do? What math? I would have to use Pythagorean theorem. I would literally have to go 109. We'll do that. Let's do that. I'm going to show you two different ways. This is the more complicated way. So if I wanted to find the area, I would first need to find this length. To find this length, it would be the square root of 109 squared plus 1 squared, right? Because this would be 109 units this way, 1 up. On the top of y'all's head, what's 109 squared? Don't think so. But that's a good guess. Or is it? Well, I know 100 times 100 is 10,000. So it's got to be more than that. But I wish the 9, I don't think it works as easy. What is it? So 11,881. So you had the some of the parts, right? Yeah, yeah, yeah. And then what's 1 squared? 1, right? And then if I added those up, I get 11,882. That would be this guy's length. I'm going to keep it like that for now. Then I would have to figure out I don't think it's going to come out that easy. What is the square root of 13 times the square root of 11,882? Or you could just simply just do 13 times 11,882 and then take the square root of it. What's 13 times 11,882? Take the square root of that number. 393 even or decimals? Oh, I found the length of that this side right here. This would be the square root of 13 because 3 squared is 9, 4 squared is 4, or 2 squared is 4, then 9 plus 4 is 13. But you got 300 and something. What is the area of a parallelogram? Oh, it's diagonal times diagonal. All right, we're going to scratch this. Good thing we use pencil, right? Bathroom, that's fine. All right. It won't work because I was trying to take this as the area of a rectangle, but this is no longer a rectangle. This is a parallelogram. To find the area of a parallelogram, you got to find the area, or you got to find the diagonal links and multiply the diagonals. So to find the diagonal links, I got to figure out what this guy is. And so same process. This would be the square root of, I can't just do straight up 112. I have to do 112 minus 3, which will give you 109. Oh, because that's the point here. So this is the point 112. This is the point 3. So I have to find this length. So that's just distance. So that's 112 minus 3, which is 109 squared. Plus, I got to find this distance. So if this is at -1 and this is at 1, how many numbers from that's 2? So that'll become 2 squared. So it's kind of close to what we were doing earlier. You would take the 11,881 plus 4, and that would give us 11,885. Go ahead. Oh, you're right, because it goes slightly up. Oh, you're right. So we're not completely wrong. Because it's technically here. It's not going to adjust the 3 to 112. That's still going to be 109. But you're right. The height of this to get this diagonal here would be from -2 to 1, which would be 3. So that would be 3 squared. So this again would be 11,881 plus 9, which would then give us 11,000. Parallelograms are just two parallel sides. This guy's parallel to this guy. Because the slope would be the same. So if we do rise over run from one point to the next, oh gosh. So it would go, you would go up one over 109. And so then you go up one over 109. And then you could technically reverse it because it'd still be the negative. You could go, yeah, if you go up one, up 109. So then this point would correlate with that point. Yeah, so the slope here would be down 2 over 3. This would be down 2 over 3. To 1 to -1 is down 2. But you don't count 1. If you start there, it'd be 0, then -1. So you're still going down 2 over 3. So these slopes are going to be the same. And then this slope is the same because this still goes up 1 over 109. So these are parallelograms. Yeah. But I got you. My drawing's probably not the best, but it does make a parallelogram where the two lines are parallel. All right, so I get 11,890. And then we got to do the same thing for this diagonal. Let's do that in a different color. Lots of straight lines. So I got to find that diagonal. I build a triangle, goes up as such. And then nice. Well, I don't need that. I don't need that far apart. But that would give me, oh, I guess I do. Yeah, I would need, oh my gosh. Now hard it is to draw a straight line. Something like that. Okay. Oh no, because I want this diagonal. I can build a triangle, I guess, like this. There you go. Let's pretend that's a triangle. Holy cow, that's bad. Let's try that again. So a straight line. There we go. So there's your triangle. So to find that length, I got to find this height and that length. So this height would be just 1, and then this would be 112. So this would then be the square root of 112 squared plus, well, doesn't need a negative, 1 squared. 112 squared is 11,144. Is that going to work out the same? I'm going to go with 11,000. No, 14,441. Dang, what is it? I was wondering if there's a pattern. 12,000, what? 44 plus 1. That gives us 12,545. All right, so with a parallelogram, now that you have your two diagonals, multiply these two guys together and take the square root. Curious what you'll get. Let's see if we're right. Do that. So 12,540. So a parallelogram is diagonal 1 times diagonal 2. That's how you find the area of a parallelogram. Bless you. Diagonal 1 times diagonal 2. So that the green is diagonal 1. So I've made a triangle to find that length. The blue is diagonal 2. So I made a triangle to develop that length. So I just need to know 12,545 times 11,890. Yes, sir. Gosh, shouldn't it? It should be, right? Parallelograms are supposed to be the same. Oh, no, it doesn't have to be. That's a rhombus. A rhombus has the same equal diagonals. Gotcha. No, a parallelogram does not have the same diagonal. Gotcha. No, yeah, you almost have me there. What was the number? So 12,545 times 11,890. Yeah, what's the square root of it if you got that answer? After you took the square root of it? That doesn't seem right either. I don't like your judgment. Again, your judgment, not really taking it. I'm gonna have to Google the area of a parallelogram. I'm pretty sure it's diagonal one times diagonal two. Area of because I go through y'all first. Yeah, it's oh gosh, it's base times height. I did so much math for no reason. Oh, I gotta love this. All right, so base times height. So I just gotta figure out how long it is. No, it's 112. It's 112. For, height would be 3. Let's do this. What's 112 times 3? That's 336. And you are saying 109 times 2, but that's 218. Yes, bathroom, that's fine. The area of a parallelogram, base times height. Is there an alternative area? No, you're not. But no, I'm not either. Yes, go ahead. Okay. What's your ideas? Well, we just found that. It was this. Right, which is right back to where we started, which is 11,802. Yes, what's your ideas? The shape of the image is parallelogram. Correct. Yeah. Yeah. But we're on part 3. What is the area of the image? Or part C, sorry. So you take 103. Where'd you get 103 from? Yeah, 109. Okay, but that's 109. Then what? The 110? Right, we did that. That was the square root of 11,482. No, plus the 1 squared. Well, that was 2 squared. No, it says base times height. Well, yeah, if you turned it into a unsolvable. No, nothing's not unsolvable.
Here, this is 109 units to this point right here. This is from here.
It's not 109. It's not 109. 109 times 3, 109 times 2 would be what? Is 218. That's incorrect.
So then the area is 218.
That's incorrect. The answer is 221. Yeah. That's what I'm trying to figure out. Yes. A rhombus would be a square that's flattened in a diagonal. So this is like a square has like side times side, right? Because it's the same thing. So it's s squared. So a rhombus would be the same concept, diagonal squared, right? I've always been taught that parallelogram was diagonal 1 times diagonal 2. Well, that didn't work out. Google says the area of a parallelogram is base times height. Yeah, which is the length of the rectangle and the height of the rectangle. Not paying attention? Hmm. The area. Yes. So what you do? That's where I'm leaning towards now.
To be able to find this and this, and then I did that, and it's that, it's this turns that, right?
What you get? It doesn't. I was just going a route to make this a connection with a thing. It tells, okay. So here's the area of this guy. Area using determinants is what this is called. How do you spell that? Determinant. All right, so this is the part that you need to know. I was trying to make a connection with the Pythagorean theorem. That didn't work out. It happens. All right, so here's the short way. All you gotta do is find the determinant of this rectangle or the determinant of a matrix. And the answer is going to be A times D minus B times C. Sure. Oh, sorry. The other side of the absolute value. Because area is always positive, so sometimes you can get negative. That's how you find the area. So without actually taking any of these points, I can take what I was multiplying by, because this is my A, my B, my C, and my D. This is really going to bother me on how to find this parallelogram. This is what I'm going to do during lunch. So all you got to do is 109 times -2 minus 3 times 1. Figure out that result. What is 109 times 2? Good. -218. Minus was 3 times 1. What is -218 minus 3? -221. Very good. And then the absolute value of -221 gives you, there's your area. You can't see that. 221. That's the area. But it's bugging me that our parallel absolute value would be the distance from 0. So -221. That's what the book is saying. I was trying to make a connection with the Oh, no. It is just go straight to this. I was trying to make a connection with y'all with Pythagorean theorem. Yeah, distance is always positive. Yeah, you don't ever tell someone I'm, you know, -5 feet tall or something, right? You're always, even if you dig a hole in the ground, you're still 6 feet below ground level, but it's still a positive measurement. All right, so that's pretty much it. So that is the moral of the story. Make this a note. How many? Oh, perfect. We got enough time to do some more. I might come back to this later. Oh, we don't have any units, so it'd be units squared. Yeah, I think that it's just counted as like U and then square when you're not given units. All right, so calculate the area of the image by enclosing the image in a rect. So this is the point that I was trying to get to. Does it have an image for y'all? I guess not. Okay, this is what they want you to do. So it says calculate the area of an image by enclosing the image of a rectangle by subtracting the area of the surrounding right triangles. So if I had, well, I'm not going to touch that again because until I figure out how to do the parallelogram, it's going to rack my brain. But to find the area with knowing what we know, we can just simply find, so we'll just cross this out for now and go to B. To find the determinants, I can just take, now granted these are letters, but this is still your A, B, C, D, even though they're different letters. So in the formula, it's the absolute value of A times B or A times D, which in this case was A times A squared minus B times negative B. Define the area. Oh my goodness. All right, so this is what you're trying to do. So here's the image to give you a better idea. I can't draw what it's trying to tell you in a straight line. So you have a square, maybe. Here's your square. And you're trying to find this area. And the information given to you is this is A, this is B, this is A, this is B, this is B, this is A, this is A, this is B. So you have your first coordinate, which is really bad drawing, but this should be 0, 0. Because if you take our original point 0, 0 and multiply it to this thing, it's always going to come back. If you then take the point 0 or 1, 0, multiply this point, you end up getting AB. It's just going to be these guys. And then this right here would be the coordinate 1, 1 times this. So we add these up. So you end up getting like A plus negative B, which is A minus B, and then B plus A, which so B plus A. It's again just taking those 4 points from the unit square, and then this one would be, what's the last one? 0, 1 times this, which would be this column right here. So that would be negative B, comma A. So that's basically what this is telling you. It's taking that original square and then transforming this, and it wants you to find that area. So then we're back to what we were just trying to figure out in the previous one. Now we're trying to find the area of a parallelogram. And I've proven that I can't figure that part out. But what we have proven is that I could take the determinant to find the area. So we saw that if we take A times D, which is A times A, we get A squared. And if we take B times C, that's negative B times B, which would be negative B squared. So that makes that a positive B squared. with absolute value around it. And really and truly, you could drop the absolute values, and since you're technically correct right here, but any number that you plug in squared will always come out what? Positive. So you could just write it out as a squared plus b squared. No, it'd be a times a. So yeah, you could say, yeah, you would say, you don't have to, just looks cleaner to say a times a, but you could technically write it as a times a minus b times negative b. And then that goes up to that point, which then simplifies out to the other side. All right, so let's wrap up a lot of this stuff. Again, don't stress about the parallelogram. You can always just use the determinant to find the answer. But it is going to bother me. Absolutely. The biggest thing, absolute value of a times d minus b times c. That's the only thing you're supposed to get today. I was just trying to go further. I like the challenge. All right, but part 3 says wrapping up the questions and stuff like that. It says we have looked at several general matrix transformations in module 1. We answer the questions below about these familiar matrices and explain your answer. Part A says what effect does the identity transformation have on the unit square? So if I take the unit square and I multiply it to the identity matrix, which recall is the 1, 0, 0, 1. What effect does it have? Doesn't change. And what effect to the area will it have? Doesn't change the area. So I'm going to go, let's do this. Doesn't change shape or area. Okay. And we can confirm that using the determinant. What's 1 times 1? Minus, what's 0 times 0? What's 1 minus 0? What's the absolute value of 1? 1. So if I put my effect to the area and I got 1, what's the original area of a unit square? 1. So we can see that it did not change the area, nor will it change the shape. Part B says, how does a dilation with a scale factor of k change the area of a unit square? Well, first, let's think about that. What would a matrix look like? And a lot of you are getting this wrong. I need y'all to reflect back on, I think it was lesson 23, where you had, no, 21, when you had to do 8 questions. If you have a scale factor of something, what is my, if it's just a straight up scale factor, like a straight dilation, what will my matrix look like? In this case, let it be K. It would be K, 0, 0, K. You are correct by saying that, but we take the K times the identity matrix of 1, 0, 0, 1. That's how we first learned about it. And then when we distributed it to everything, we ended up with this guy right here. So this would be the guy I would multiply to my unit square values. What would then be the area of this effect? What's the area if I multiply by K, 0, 0, K? Nope, not just K. What's the formula? A times D. So K times K is what? What? K squared. 0 times 0 is still 0. K squared minus 0 is, and then I can just drop the absolute values. So regardless of what the scale factor is, it's going to be that squared. And last question, and then I'm done. Sorry for delaying y'all with the parallelogram. But does a rotation with no dilation change the area of the square? Yes or no? No, it doesn't. Because we've learned if you have a square and I'm just moving it, the shape has not transformed. It has just rotated, right? So if it's just a rotation with no dilation, there is no effect. Y'all enjoy the rest of y'all's day. And again, I do apologize, but